So as Igor mentioned, we don't think of energy well because we imagine that somehow we make it, but we don't. So if you have to take a voyage with me, so to speak, and just a step backwards into a different time when we thought energy was basically all over. A lot of people still do. You think the energy here in one place is different from the energy someplace else, and just they're kind of different things, but they're not. Energy is energy is energy. And there was a bookbinder in London 2 centuries ago, and he realized that all energy was interconvertible. Kind of invented the electric motor in the process, and certainly the practical understanding of electronegativity. But there's energy is energy is energy from thermodynamics, from running steam engines. We learned it. But this is a 10 cubic centimeter, 10 millimeter pipette. Almost hard to believe, but just this much, and I'll show you more of this in our field trip section of this later. 1 cubic centimeter, enough oil to fill in the palm of my hand. This is oil now. You got to mine it from the Permian Basin or from Iraq or someplace where who knows what the politics are. But the point is that basically it has to come from under the ground. It's a fossil fuel, irreplaceable in a way and limited. But a gram of water takes with it 580 calories, enough to cool more than a pound of stuff by a degree Celsius. And the amazing thing, Igor just indicated this kind of connectivity. Take that 1 gram, about 10,000-ish calories. If you took, now they have 2 of these things here. Imagine one being full and the other one just being 7 grams. So basically 17 cubic centimeters. That's the same energy content as a gram of oil. So 17, right, you need more of it, but water is infinitely present on Earth and oil does not. And you don't need to fight as much over water, although we've done this certainly in Mexico and everywhere else, Colorado, California, and on and on. But literally right now, every single day, basically there's more evapotranspiration planet-wide than the total energy use on the planet. It's all done literally by the power of leaves, but also roots. But we're forgetting something, of course, which is soils, because water falls out of the sky and it would just run off into the oceans as it did a mere, let's say, 3 billion years ago. But then come around, you know, the type specimen here, I have it someplace, around 420 million years ago, you started to get plant life across the whole surface of the Earth. And then below those plants, they broke down. They were coupled intrinsically with bacteria, with fungi, with prototypical annelids. So basically they made a material that didn't break down quickly. Refractory, I'm looking to see if there's any here, we'll see some later, but basically soil, which is a kind of web that holds about something like 1/5 of its weight in water. And that water is basically what runs the whole biosphere. So every time you see an organism, like for example, those plants outside, those are entirely made by the flow of water through the leaves, and that's facilitated by soil, which captures the water, holds it, and solubilizes nutrients, moving it to the plants. Where's the energy come from? Well, 2 places really. One is what I just described, and you have all felt it. Every last one of us sweats. And that's the only way you can stand out in the sun, and you cannot lower your body temperature basically by simply moving through hot air, because you'll simply pick up more heat. But remember, if a gram of water evaporates and it takes with it 580 calories, then take your weight, roughly speaking, you would need about that many grams of water, a little less, to drop your whole body temperature by 1.8 degrees Fahrenheit. So from say 102 to just about 100, in other words, or say 100 to just about 98. In other words, you might survive, and that's the way we do it. Temperature, of course, is a critical parameter, variable for human beings. And the temperature on the planet is not set by the air conditioner, although in a way it is. But the air conditioner is not the thing we built and put in the window. It basically is the climate regulator of the plant itself. So look at a map of the globe maybe later on and see what the average temperature looks like. It's almost hard to believe, but the highest radiation, if you take a globe, highest radiation is going to be around the middle, around the equator. But that's the temperature there are not the highest. They're the highest, of course, in Siberia or the Kalahari Desert or the Sahara, but not in the Congo or the Amazon. And the reason for that is very simple, because basically the hot air is boiling off the top leaves and cool air is dropping off the bottom ones. So Igor, could you show that exquisite Schlerin, this is Schlerin photography, which is basically a way to visualize heat flow by using the density differences of the atmosphere. And there you can see the plant is cheating on the temperature side. It's basically dropping cool air because it's evapotranspiring. It's evaporating water. And that's making the air around the leaf denser. And it therefore is dropping into to the floor of the rainforest, to the floor of the locale of the forested landscape. The tree has got to be, the tree would simply be a black body radiator, as you'll see in a second. If it did not have water, but with water it becomes a transformer. So more cool air coming off a pine tree. David Gates, my professor for a period of time, I did part of my thesis in the boathouse at the University of Michigan Biological Station. I recommend this as a way to learn anything. I was working on mosses and the like, but if you can see, and I think we see the equation in a bit, you can literally see that the Central Park works exactly like this when it's got water. Prospect Park, every street tree, I see Karen Argenti on this, and we built streets along the Bronx, basically trees doing the same thing. If you had enough of them, and there's hot air boiling off. So if it's a 95-degree day, that leaf is something like 102. The other leaves, of course, if it was a 95-degree day, they'd be something like approaching 80. So I am not kidding. This is the thermal regulator that's running the planet. We are not all dead because that is basically conveying carbon down to the roots and into the soil, into the microbes, into everybody who lives down there, which is the largest population on the planet by a long shot on the terrestrial side. So still air, again, white pine, Pinus strobus, beautiful creature. And you can see she's hot, and hot air is boiling off. Again, that surface area is great for shedding snow, but also it's partitioning the heat at the same time. Same thing for the spruce. So every time you see a tree, remember that there is work there, and it's work on the energy side, and that's building the soil through a number of steps from top to bottom. So, and the bur oak, I've got this area where I am wants to be a pin oak forest, but oak is basically a relatively, well, they can live in wet or dry areas, but they are very stable against heat loads. So that is the only story there is, in a way. Is the equation on there someplace, Igor? Could you show that someplace so people could just see? We have that. It basically, it just says input equals output, but the two big parts of that are essentially the physical piece, which is the hot air boiling off, which is basically just the physics of exchange. It's what makes the urban heat island. When objects heat up and heat the surroundings, they create higher temperatures. When plants heat up, they actually shed up to 10 times as much energy with that cool air falling from the leaves.
I'm still working on it to open up a new presentation to get to the equation.
So it just, because I know you'd be very disappointed out there if you signed up for this thing and not a single equation for an energy, that would be a you'd probably ask for your money back. But anyway, the nice thing about it is that equation makes it's from those photographs, from those CERN pieces, you can actually see what an equation means. And what it means is basically there's energy in, total energy in, and that's partitioned into the energy where the heat boils off, into the energy where the heat actually drops down. Let's just say heat is transported into latent heat or evapotranspiration. And then there's respiration and photosynthesis, but they're only about 1% or so of the total energy flow. So it's good to see in a way that there's a way to formally get a hold of all of this. And if you do, then basically what human beings do with energy planet-wise is not insignificant. It's just a small part, very small fraction of what the planet does herself. So this isn't absolutely critical. We can find it later. But
I got you, Paul.
Yeah, good. So there it is. This is arranged in a way. So Rn is the total radiation load, and basically you can easily move the sensible heat H. The G is basically the a fraction, but it's also the heat that's moved into solid stuff. But the two big parts are the H and the LE, basically the latent heat. And then respiration and photosynthesis, R and P, relatively small. So total energy, input and output, minus one another equals 0. I usually like to show this equation so that the radiation comes in on one side and it's partitioned on the other. But the point is, we could make cities like that. And right now we make them so that we get mostly H out and we all suffer in summer. And there's no leaves also, though all that beautiful leaf area also pulls particulates out of the air and essentially makes you live longer, because the 2.5 particles stick to the leaves a quarter gram a year, as opposed to your and my lungs. So let's go on now. So I'm just talking about actually the dynamic part. So if it takes about 17 parts of water to cool the environment, ice actually, when it freezes, heats the environment, but it's only 80 grams per cc that is 80 calories per gram instead of 540, but it's still significant. So that's the reason the city hovers around 32 until all the water is frozen, and then it gets much colder, depending. But the other part of water is latent, is basically its tremendous capacity to hold and lose heat. And that's the only reason we haven't completely melted the iceberg so far, because the ocean is an enormous sink for heat. And all of the excess heat that's been produced, most of it is in the ocean. In other words, water has got a capacity to hold on to heat. And Igor will tell a story about how that could be used, again, to largely entirely, greatly, more than basically to change the energy budget of every city, including this one.
Thank you, Paul. That was wonderful. So we're going to move into an interesting conversation. One of the let me just give you a little backstory. I was in a call with Tatiana and George. Just, we're going over the basics, just planning the symposium, and Shannon said, we're going to have a workshop on Saturday, October 3rd, and it's going to be about soils and energy. And that was really really funny, because Paul and I were just working on a practical application for a city that I cannot name. For competition reasons, I cannot name this city. But so when you see this document, you'll see that there are multiple redactions, as if we're reading some classified CIA piece that was leaked from WikiLeaks or something. But essentially, I'm going to open up this presentation right now, and where is it? There we are. And we're gonna, wait, what is this? Sorry. We'll close that out. All right, let me, oh, I did not share my screen. I apologize for that. 1 second. I'm getting technical issues from having too many presentations open. There we are. So I'm going to share my screen and kind of show you an application, a very practical application for using the energy of water through soil or a soil-like substance to essentially solve an issue for a city. So I'm just going to keep referring to it in vague terms as a city and not as for obvious reasons. So, you know, the first part of this workshop, what Paul's describing was a way to combat the urban heat island effect. And so the takeaway here is that plants, when supplied with water, if they have a sufficient leaf area index, meaning that if it's over 3, meaning that the plant's leaf area is 3 times higher than its footprint, if those plants are supplied with water, they will produce they will produce cool air that's equivalent to about for all 224 square feet of these plants is equivalent to about a ton of air conditioning each day. So on the graphic on the right, you'll see kind of what that translates to from a green technology perspective. I made this graphic a few months ago. I thought it was pretty good. You can kind of see that Central Park is 80 degrees Fahrenheit. So let's assume, but assuming the temperature is the same throughout the city, which it would be, places that are covered with 50% green on their surfaces, so let's say green walls and green roofs, will be 82. At 25%, 86 Fahrenheit. At 15%, 89 Fahrenheit. And at 0% green coverage would be 92 degrees Fahrenheit. So essentially, plants produce cool air. And this cool air literally changes the climate of cities. It's such that you don't really even experience an urban heat island effect anymore. And about a year ago, the city of New York, so 7 city agencies, the Danish Clean Tech Hub, and a few other groups have held a competition, which was, it was called the New York Access Cities Open Innovation Call on air pollution and urban heat island effect, right? That's a mouthful. And they essentially wanted a solution to the urban heat island effect that's both feasible and effective. So we proposed this solution. And the solution could basically be summarized in this image right here, or rather, if you want to speak about this much more lengthily, maybe you'll have to join us for a different workshop, maybe not. But I can send you the full presentation later. But after that, you know, Paul and I co-founded a company called Leaf Island, which builds green technology for that's both modular and scalable. Essentially, green technology that works. We don't do greenwashing. But you know, in the early stages of a startup, you're always looking for ways to get ahead, ways to you know, get capital. And so one of our ways was to enter competitions that actually challenge ourselves to come up with new solutions. So this one competition came up, and the purpose of this competition was that we needed to heat a city, not cool a city, but heat it. How do we heat a city using green infrastructure? Because you know we're used to, because plants produce air conditioning, right? I mean, how do we reverse that? Like, what sort of solutions can you propose to make the city actually warmer without using fossil fuels or solar or nuclear or wind energy? How do you heat a city? And you know, Paul's a pioneering green infrastructure expert and a plant biologist. I can go through his resume. If I were to go through his whole resume, it would take me like 40 minutes alone. And he had been talking about building aquifers for New York City under our streets and our parks. Essentially, you dig pits, you fill them with recycled glass aggregate or concrete aggregate or something else, some other aggregate, and they are to store stormwater runoff. He's been talking about building these things for the last, as he informed me, since '95. I was born in 1992, so he's had this idea since I was 3 years old, and now, Paul, this crazy idea that we can use these stormwater aquifers to warm a city, and so we just kind of ran with it, and we kind of talked about the science, and we designed it. We designed it, and we entered this competition just last week. So I'm just gonna go through it. Hopefully, hopefully it's easy to understand. But once you see more graphics, then then you'll truly kind of be able to appreciate it. I know there's a lot of redactions and security clearances. This is all for fun, but essentially, this city has some pretty lofty goals. They want to. They have a cold climate, so their problem is that they spend all this energy on just heating the city, and because renewable energies are not as efficient as we'd like them to be. Unfortunately, a lot of that energy comes from coal. Some comes from natural gas, and then they use heat pumps, biofuels, fuel oil, and a little bit of renewables to meet this heating demand. But they said, you know what? We're going to take our coal plants down by 2029, and we want to be completely carbon neutral as a city by 2035. That's a tall order, but most people will say, yeah, we have to build like 20 solar plants to meet that. We have to build 30 wind farms. We have to do this and do that. But our idea involves neither of those things. It's actually quite simple, and it is a soil and energy solution. So the idea was to build some of these stormwater aquifers, right? And these stormwater aquifers would essentially go under roadways, they go under streets, and they would fill up with stormwater. And because this is a cold city, they fill up with snow melt as well. It snows pretty often over there. So, and once they fill up with water, they're now in the ground, and the ground insulates rather everything inside of it. It's something like 50 to 55 degrees Fahrenheit in the ground, no matter where you are, whether you're in the equator or whether you're in like Iceland or something, or Canada. It's always going to be 50 to 55 degrees below the surface. And that's just one of those rules you play with when you're playing this game of green technology. So these aquifers would fill with water. The water, and there'll be two parallel air tunnels in these aquifers. And I'll show you the drawings in just a moment. And these air tunnels would, the water would conduct heat to the air, and the air could then be pumped into houses. So houses can start with a temperature that's 12 degrees Celsius, which is about 55. The city uses the metric system. So as much as I love feet and the Fahrenheit and inches and all that, I had to use metric for this presentation. So and these aquifers would essentially give us a start point that's a lot higher than whatever the start point they're using, because between because it can get pretty cold in the winter. You get to like negative 10 Celsius in the winter. But if you're getting air from these aquifers, that's nearly limitless, and it already is 12 degrees Celsius. All you have to do is just heat it to 20, and now you're at room temperature. 20 degrees Celsius is 68 Fahrenheit. That's your room temperature. So what does the city do now for heating? They use something called district heating. And district heating is kind of like something you might hear from the Soviet Union from back in the day. You know, I was born in Ukraine, so I'm not unfamiliar with these types of centrally planned setups. But essentially, in this city, you have a energy plant, which is represented in this chart on the top. The energy plant does three things. Well, two things rather. It burns some sort of fuel to produce power, and also produces heat. It produces hot water. So the plant essentially boils water and sends electricity to houses. The hot water goes to these residences. And this is what a district heating system is compared to, like, you know, having boilers or water heaters in your house, right? So the hot water starts off at something like 110 degrees Celsius. It's very hot. Like, we're talking hotter than boiling. So it's under pressure, so it doesn't just evaporate. And it's sent to houses, and it loses so much heat. And you know, imagine you're sending boiling water through a 2-mile long pipe in the ground that's 50 degrees, just for it to get to the house. It arrives at something like 60 degrees Celsius. Each house has a heat exchanger in the basement. So the heat exchanger takes basically takes the amount of water. It transfers the heat from one portion of water to the other portion to get it hotter, because, you know, everybody wants hot water in their showers and they want hot water in their pipes. You know, because everything's it's a steam heating system, kind of like having a radiator. So the heat exchanger partitions this hot water coming from the plant into two pieces. Some of it, one piece, the hot piece goes towards into your shower and into your pipes, and the colder piece goes back into the cold water side, and it returns to the plant. So that's interesting, because this water, I call it cold water, but it's really not that cold. It's like 40, 50 degrees Celsius. But by the time it goes back to the plant, you know, it's really cold. So then they're heating it again and sending it through the hot water pipe again, and, you know, this is a cycle. Our system says, you know what, like, screw that. We're not going to even have a hot water side. We're just going to pump cold water to the plant, no heat loss because you're not heating it. And you can use a water heater inside a house to heat the water from there. You don't need to have a heat exchanger. You can just use a water heater and heat it on site, so there's no heat loss, right? And the heating is going to come from the aquifer itself. We're not going to use water for heating anymore. We're just going to use air, because this air starts off much warmer. Because, as Paul mentioned, energy is energy. You know, if you start off at 12 degrees Celsius, you're automatically saving money than if you start off somewhere colder. You're saving on energy. You don't need to, you know, produce as much. So the aquifer is full of basically a limitless supply of 12 degrees Celsius air. And it's going to, there's going to be a heat pump inside the building, which simply partitions this air much like a heat exchanger, and it gets the air to 20 degrees Celsius, and it heats the homes instead. So yes, the heat pump and the water heater use energy as well, but much less than the previous solution, because there's no heat losses, and you're starting at a higher start point. So this diagram kind of shows you the cross section of the aquifer, the temperature regulation aquifer that goes under roadways, right? So you have your 3 meters of it's 3 meters deep, so about 9 feet. The roadway is on top of it. There is a layer of cemented gravel that kind of doesn't freeze in case, you know, it gets really, really cold during the winter. And it also just keeps the road more reliable. You know, this is kind of how the Romans used to build their roads, and they're still around today. So, you know, they use cemented gravel underneath their there's the stone. So the aquifer is filled with recycled glass or concrete or granite aggregate. And granite aggregate is very common in this part of the world. And all it does is capture stormwater, right? And then you have your two heat tunnels that are separated by a concrete slab. And the heat tunnels, so when, let's start here. It's -4 outside. You have rainfall or you have snow melt, more likely. It goes through this tunnel, fills up the aquifer. The aquifer, through conduction, transfers heat energy to the air inside these tunnels. Then the air is pumped out by the heat exchanger, by the heat pump inside the basement of the building, and goes up as 20 degrees Celsius air. And the city also happens to have a tunnel network, which you can always transfer water to in case aquifers get full, but we don't think they will because their capacity is very high. So you can use it under roads, or you can use it under parks. So here's an example of a temperature regulation aquifer under a park. And the beauty of this one is that it works much the same way as the previous one under the roadways. You have your pipe that takes the air out of the tunnels. You have your air tunnels that are made of concrete slab, and this is a very stable design. But instead of there being, a paved surface like in this one, now there is soil on top. And on top of this soil is a wetland. And the wetland does this beautiful thing of taking up carbon. In fact, a fully developed wetland takes up 2 kilograms, or about 4.4 pounds of carbon per year per square meter. Okay, so a 300 meter, so a 960 foot by 100 meter, which is like a 370 foot wetland. It's not that huge. That's like about the size of a small park. That takes up 60,000 kilograms of carbon per year, or about 130,000 pounds. So, if your goal is to be carbon neutral, the point of you can be carbon neutral by having the system be carbon neutral, not just each technology somehow being carbon neutral, because that's not really possible. But if you're generating carbon on one side, but you're taking it up on the other side, because that side is carbon negative, it balances out. That's why you have a carbon neutral system, or even a carbon negative system, if you can balance those metrics out. So next, I'm going to talk about the co-benefits of this in a bit, but I just want to show you how this would look like on the map. So this is so the green are the aquifers, the green lines. The yellow lines are the air tunnels, and you can kind of see that the air tunnels connect to the buildings in the kind of yellow-orange circle. So you can kind of see that over here. And so each building has 1 or 2 connections depending on what the demand of this building is for heat. Larger buildings should probably have more connections. And so I want you to think about this as an underground fire hydrant for air. For people that don't think it's feasible, I mean, look how many fire hydrants there are. That's feasible. So why not have a fire hydrant for an air hydrant that connects to another pipe? And this big red circle over here connected to the park, that's an air tunnel intake. So it's not going. You need to balance out the negative pressure. If you have all these buildings sucking air out, they're not technically sucking it. They're more like partitioning the heat out of the air using a heat pump. But there's still going to be some degree of negative pressure that has to be equalized. So that's why you have an air tunnel intake in an area that's kind of could be closed off. So let's talk energy. Let's talk let's talk numbers, because nothing pisses me off more than when people come up with green solutions, but they can't really justify the math. We have to come up with, if we're going to ever, deal with climate change, deal with environmental issues, we have to have realistic solutions that are both feasible and that actually, make engineering sense, make mathematical sense. So this city was kind enough to give me a heating demand profile. So this is the amount of energy that people, let me just check my time. Okay, I'm still on time. This is the amount of energy that people used throughout the year of 2016. And you can clearly see that the demand increases during the colder months. So it's the highest in January, February, then it's pretty high in December, and it's pretty low in June, July. So we want to think about how much energy is this going to save, right? So the way we did this was, if we assume that the air coming through the air tunnels is 12 degrees Celsius, and it's going to, it's basically limitless at that temperature. It's going to essentially make it so that the energy is constantly 12 degrees Celsius, right? So I took the average monthly temperatures of this city, and I noticed that it's about 12 degrees Celsius in April and October. So that's going to be like the maximum. That's going to be the maximum temperature that you're going to need to heat from. So, and we know how much temperature they need to during April and October. We know what their demand is for energy, for heating energy during those months. So let's assume that this is consistent throughout the rest of the year. So we can cut these peaks off, right? We don't need these high peaks anymore. This orange line is going to be what the energy demand profile is going to be, because you're heating from 12 degrees Celsius. You're no longer heating from -8 or -26 that is outside, that you're pumping all this hot water in just to fight against. And that, if you look at the peak energy, the peak capacity for the city is 3,600 megawatts, 3,630 megawatts. If we cut the peak demand to 500, maybe 600 megawatts, then the only capacity you need is 900, because you always want to have excess capacity. You never want to push it too close, because you don't want to have any issues that they're having in California right now with the energy grid. So let's assume we're going to cut the energy demand to 900 now, just to be safe. That's a 75% decrease in energy capacity. That's really substantial, because, and you'll see why in a second, why decreasing the capacity is important, more important than the usage. And if we were to integrate over this curve and just get a percentage, this area integrates to about 30 to 40% energy reduction. If we were to remove this area from the total, like navy blue of the curve. So if you do just a mathematical integration, you can remove a lot of this. So we're talking 75% decrease in energy capacity and 30 to 40% decrease, total reduction in energy usage, just from digging aquifers underneath the streets and getting hot air from there. And that includes the inherent efficiency of using modern technology, because the system was designed in the 60s. This is the district heating system they're using. So the technology's gotten a lot more efficient than in the case of the water heaters and the heat pumps. So if you know how a wine cellar effect works, if you've ever been in a wine cellar, you can see how the energy is just constant all year round. This works using the same principles. So we call it the urban wine cellar effect. So what does this mean for the energy profile? This is what they currently have. All right, so they're using natural gas, they're using fuel oil, they're using coal, they're using pellets, which is basically biofuel, and they're using a heat pump, which is renewable. And they're planning on taking their first coal plant down in 2024, and they're going to replace it with about 360 megawatts of mixed heat pump, geothermal, and biomass. Right, so if we cut their energy capacity by 75%, this is what's going to happen to the energy curve, to the energy budget. It's when we factor in the proposed increases already to the orange and the green, which is the biomass, we don't have to use coal at all. We don't have to use fuel oil at all, and we can cut the natural gas significantly, because that's of the three, that's the least carbon, that produces the least carbon emissions. So cutting capacity, a solar plant and a hydroelectric plant and renewables can run all year round. So it's not about total energy usage. That only affects the end user. It's the capacity that's difficult to deal with, because renewables don't have high capacity. They don't have the capacity of a coal plant or any fossil fuel plant, or especially a nuclear plant. They just, it's not realistic to build 10 wind farms or 10 solar plants, right? So if you can cut the capacity, then you can only rely on the renewables more realistically now, even if they're producing energy all year round. So it's really cutting the peak capacity which we're worried about. That's what's preventing us from shifting fully to renewables. So what's next? So here are just some of the co-benefits, right? So it's not just the energy that we're worried about now. We can get stormwater mitigation. These things capture all the because 300 meter by 10 meter street, that's the width of a street. If we multiply the depth of the aquifer, it's a 9,000 cubic meter temperature regulation aquifer, which has 22. Once you do all the other engineering calculations, you get 2,700 cubic meters of static stormwater capacity. That's a lot. Okay. I don't want to do the conversion to gallons right now, but it'll basically capture 100% of stormwater. Same thing, 300 meter by 100 meter green space aquifer in a park generates 52,000 kilograms of carbon capture each year. The reason it's not 60,000 because we want to have paths, we want to have walkways, we want to have benches. You don't want to just be in a wetland, right? So not all of that land is going to be used for wetland. Some of it just has to be given away to pedestrians. So this would completely redesign. It would completely change the biodiversity aspect of this city, because now you're creating green corridors. Most pollinators and birds, they don't travel too far from between parks. They only travel about 2 kilometers, about a mile. So if you create more of these green spaces and wetlands that are they're incredibly productive, you're now allowing them to move around much more readily, and that's going to do wonders for the pollinator and bird populations. What about the resources? What are all these aggregates coming from, right? This process is self-sustaining. So all we need is stable aggregate. It could be concrete, it could be granite, it could be glass, it could be brick. It doesn't have to. All it has to do is be chemically stable, so it's not going to dissolve under rain conditions or whatever. So it can't be gypsum, right? And it has to be clean, so it can't be contaminated with, like benzene or something. But if it meets those two requirements, which are not very strict requirements, you can use that aggregate. So let's say you're going to do a road repair. You're going to dig out the street. You're going to generate 9,000 cubic meters of aggregate right there, basically. You're going to fill it with 6,750 cubic meters. Now you have enough aggregate for the next one, and the next one, and the next one. And you're actually, it's not just self-sustaining. It's self-generating. Like you're generating extra aggregate by building these things, because not all of the volume is going to be aggregate. You need to put the air tunnels in too, which takes up 25% of the volume. So what do we do with all this excess aggregate? We can build wetlands elsewhere with it. And of course, this is there's a lot of climate resiliency here. If we the thing with the temperature regulation aquifers is that you can run the heat pump and warm the air from 12 degrees Celsius higher. You can warm it to 25 if you want. But what if in 50 years it's going to get really hot in your city, right? Or it's going to get a lot warmer? What if you have more hot days? Simply don't heat the air. It's 12 degrees Celsius. That's 50 to 50. That's like 50 degrees Fahrenheit. That's air conditioning temperature. Just don't run the heat pump, and you get cool air through your aquifers now. So I don't think anybody wants air cooler than 50 degrees in their house, honestly, 50 Fahrenheit. So I apologize. I'm jumping between metric and imperial, not constantly. I hope I'm not confusing you. So, so you're basically getting this solution works in any city. It works in Lagos, Nigeria, and there are 85 million people by 2100. So that's just something to think about. That it's resilient to climate change because it works if it's hot. It works if it's cold. And of course, all the extra vegetation produces cool air, which is good against urban heat island effect. So just kind of showing that 300 meter by 100 meter aquifer producing 1,200 tons of air conditioning equivalency each day just from the evapotranspiration alone. So let's talk more numbers. How are we going to get this done? How much would it cost? So I read that it takes, I read in an engineering geology journal that it costs 100 euros per cubic meter to excavate in this city, right? So let's do some math. Let's if we're going to factor everything in, I'll skip you the headache of the calculations and tell you that 300 kilometers of roadway, and that's 10 with a 10-meter wide road on average through all the populous areas is going to cost about 1.62 billion euros over 15 years. Oh, that sounds like a lot, right? He used the word billion with a B. That's a big number now. But that's only about 106 to 133 million per year. The city of this city, I'm sorry, I almost revealed the city name. This city pays about 1.85 billion euros per year, not over 15 years, per year, on consumer energy costs. So businesses and households spend this much money on energy each year. So even if our aquifers reduced energy spending, energy costs by 6 to 7%, they would break even, right? Because if you divide this by, if you multiply this by 6 to 7%, you get these numbers. But they're not going to reduce energy costs by 6 to 7% or energy usage. They're going to reduce it by 30 to 40%, right? And they're going to cut peak capacity by 75%. So is this feasible? It's more than feasible. I'm showing you, right, this is how you argue for green infrastructure. You don't talk about vague points. You show them the math. If we assume it's going to cut this much energy, then it's going to save people almost like about $800 million a year, but it only costs 133 million, right? So that's a really good return on investment. And even if we get our calculations wrong, and it's not 30 to 40%, it's 20%. We just have to do better than 6 to 7% for it to be worthwhile on the financial side. So this will be our plan for them. This is not interesting for you. This is just how we would implement this. It's a timetable. There are some ways to cut costs. I'm running out of time. I don't want to go any longer. So because we have a little more workshop. And this is just our team. There's Paul, there's me, there's a few other folks. And that's it. So, let me stop the screen share. I'm proud of myself that I didn't reveal the name of this city by accident. I hope you that wasn't too much. We'll have a question time in a bit, and I'm going to pass the microphone over to Paul, the proverbial microphone, so that he can close out this workshop, and then we'll have a discussion section. So, oh, Paul's on his phone now. One moment, let me spotlight. Let me ask him to start the video. Hey, Paul, you're muted.
Okay, that good?
I hear you loud and clear.
All right, let me.
It's a bit of an echo.
Gotta turn the other one off.
You might have to unplug the headphones.
Oh, that should be okay.
Better.
All right. Hold on. I am going to walk out to the field trip version of this. Just give me a minute to get to the azalea in the soil.
Very nice presentation.
Thank you.
Let me flip this around.
So Paul's going to take you on a field trip.
Yeah, hold on. Let me figure out how to. There's a way to. There we go. All right. Now, this is one of the creatures we were discussing. This is a.
Paul, we can't
azalea.
see you.
Right.
We can't see your camera.
You cannot.
No.
All right. Oh, I wonder what I did wrong. Hold on. Yeah.
That's good. We see you now.
You see me, but I want you to see what's in front of me.
Oh,
You might have to
you have
point
to
the phone
turn
forward.
around. Turn around the thing.
Yeah.
There's a
Trying to
thing
figure
there.
trying to figure out how to do that. I want to stop the video. I want to.
Just turn the actual phone around.
All right.
We can hear
All
you.
right. I can. Oh, can I see this? I can't see it. All right. Well, I can see it just by looking into it. So this, ladies and gentlemen, is an azalea, and it's right outside of my study, and it basically is a. So about, roughly speaking, 4 square meters. So it's capturing something like 10-ish pounds of carbon a year. So up close and personal, this is what a soil looks like. That top layer, the leaves are broken down into this, which is almost pure humus. And probably I've had 15 different species of warbler and kinglet through this wonderful creature this year. So essentially it takes the stormwater from this house, goes down, goes underneath these slate pieces, and I will try and pry one up because you can see the first ever recycled glass aggregate underneath them, goes into this little wetland here. Some of that's recycled over that green wall. The mosses are growing down and on the other side. That orange flower is touch-me-not, so that's another hummingbird pollinated tube flower in the yard here. This creature here is a royal fern. She is at least, oh, what's the number, 300-ish million years old, same taxa. That's a mere cinnamon fern, and she's only 300 or so million years old as well. But the point is that basically that garage feeds the wetland and the soil. And again, that has a very, very, very specific energy meaning. And I'll show it to you right now. So again, I have to, let me see what I'm showing you guys. You can see these two graduated cylinders, can you?
We see them, Paul.
All right, so the one on the left has got 3 grams of water, but I didn't want to put oil in there, very, very hard to clean out. The one on the right has got 51-ish grams of water, which is the energy equivalent of 3 grams of oil, but you don't have to start a war in Iraq or any place else to get it. It comes down out of the sky every single year in huge amounts. So literally this much water, 1 gram, is 580 calories evapotranspired, enough to drop the body temperature of more than a pound of stuff by 1 degree Celsius. So that's the point. Basically, you can either, so the yard, you can see the, why do I leave those ragged sunflowers up? It's because every year, and still now, we're missing them at the moment. Oh, there's a goldfinch. Goldfinch comes and they eat the seeds. They've been here in America since, probably since the last ice age or before, and basically are coupled with these particular prairie plants. So those red flowers are not native, but the hummingbirds love them. So the point is that basically we have an opportunity always in front of us to take water, and if it was the right season of the year, I could point a heat gun at the leaves and they would be below the temperature of the surrounding air because they're in the shade. And that's just physics. So Igor was talking about a much more difficult trick, which is heating a cold city. Cooling a hot city is guaranteed, as Olmsted showed us, by simply building the biota into the fabric of the city. They stopped them at the borders of Central Park and Prospect Park. That was a mistake. We need to basically extend it across the whole city as ecological infrastructure, as green infrastructure, because people talk about climate change, but literally if you pack the trees into the streets we live on, covered the, I don't know, maybe 30,000 square foot of wall with vines and the 34,000 square feet of roofs, you would change the temperature of the planet. The notion, people would no longer know what an urban heat island was, because all urban centers would actually be something like 5 or 10 degrees below ambient through the warm season. And as Igor just described, the water that was captured through the plants by the aquifers would basically end up as your heat source altogether for the landscape. Now, if I can do this with one hand, let's see if we can take a look. You can see under there, there's basically recycled glass aggregate, started, as Igor indicated, when my daughter was 3 back in '95. And the point is that now this whole walkway is basically a water capture aquifer, only a few inches deep. I can only drink so much wine and all and break so many bottles. But the point is that we could do this everywhere. And Karen and I actually built some of things exactly like this on Stratford Avenue. Karen Argenti's on this call in the South Bronx. So the point is, we can either throw things down the sewer, which we do now, or we can turn them into one of the richest biodiversities on planet Earth, our temperate zone flora, and the fauna that goes with it, which is something like 200 species of migrating birds this season of the year, every spring and fall. All right, I'm going to go back in. Igor, maybe you can take over from here, and I'll join you in a second.
Thank you, Paul. That was a mini temperature regulation aquifer. But once we dig a little deeper and we connect it to your house, then your energy bill is going to drop during the winter.
I like this idea.
Although we might need we need to buy that heat pump. So I wonder, when we talk about soils and energy, I wonder if this is what our audience bargained for. I'll see you in a sec when you're back. Oh, I see you right now on your other screen, Paul. Okay. Well, I think that's one way to think about energy besides, how we generate it. It's like when we began this conversation, we were talking about how we can reduce energy needs of a city, because reducing energy is better than generating it, right? If you don't need something, then you can't generate, then there's no waste involved, right? And so if we do the same to cities, and so when I mentioned that technology is probably what's going to end up saving us within the next 80 or so years before we start getting 80 million population cities. I didn't mean like a new smartphone or some sort of new gadget or like or anything like that. I mean, by technology, I'm referring to the way we think about energy, because this technology which we're referring to, it's low tech. It's not smart technology. There are only a few sensors there, not too many. This stuff has existed, I would say, since possibly the beginning of civilization in one form or another. Paul would argue it's existed for 400 million years, ever since soil has existed. I guess it depends on, in a way we're both right, because we humans probably discovered this stuff 3,000 years ago, but it existed for far longer than that. So it's not about inventing new things so much as it is about thinking about them differently, and thinking about how energy differently, and not looking at this system in such a one-dimensional way or such a two-dimensional way. It's the energy is all around us. It far exceeds anything our power plants can produce. So if we just open our eyes and use it properly, and maybe make modifications so it fits our needs, like within urban populations, then we will be able to, solve the energy crisis in cities in the future. This could be the second green revolution after the fertilizer